class of periodic table. So this is the fifth class. So in this class, we will talk about the periodicity of the physical properties and the chemical properties of element. So the titles will be 1 minute. Just yeah. So the point is that the periodic tense in chemical properties. We know that in chemical properties. So in the previous lectures, you can see the physical properties. We already talked about the physical properties of the element. They are basically we have know about the atomic properties, atomic radius. Then already we have uh, seen that ionic radius, and also there is ionization enthalpy delta of H and ionization gain enthalpy, electron gain enthalpy, and also the electronegativity. So these are actually the physical properties. Now we will talk about the chemical properties. How this periodic table, in this periodic table, how this element can react with this other element. So there is any link to atoms, or is there there is no link? So to know about that, first of all, we will know about us a number of outer shell electrons. So this is the valency of an element. So now the why the 8 left came, we know that this octet rule uh, for this every element, any elements, it is a stabilized. Suppose I am talking about suppose the normal gas, but inert elements like helium, neon, argon, krypton. Uh, so these are actually the stable gaseous element, noble inert gas element. Why these are the stable? Because here the outermost cell, valence shell is filled up. If you see what is helium, this is the 1s2, 1s orbital, maximum number of electron will be the 2. So for that nears, it has the maximum valence electron, the 1s2 and 2s2, and this is the 2p6, the 8. 8 electrons is there. Now, to know that to know that the valency, first of all, you have to know the valence orbital. Suppose the neon. Suppose the neon, the electronic configuration is 1s2, 2s2, and this is the 2p6. So there, the maximum principal quantum number n equal to 2. So, uh, the orbitals is 2s and or another orbital is the 2p. So these actually the valence electrons. Sorry, these are actually valence shell. So whatever electrons will be present in these orbitals, this is called the valence electron. Here the 2s and the 2p, this is the valence shell. Now the electron 6 plus 2 equal to 8. So this 8 electrons is called this valence electrons. Now the valency, here the valency equal to 0. Because if you see, this is the 8. 8 minus 8 equal to 0. So 8 actually defined the stability. This is actually defined by this octet rules. When this valence cell is filled up by these 8 electrons or the fulfilled, then it is the stable. Now, for this element, when we will calculate the valency, then it will be the 8 minus number of the outer shell electrons. Suppose a fluorine electronic configuration is 1s2 and 2s2, and this is the 2p5. This is the 5. So this is the valence cell, 2s and the 2p. Now the valence electron, so the number of the valence electron, so the number of the valence electron equal to 2 plus 5 equal to 7. Now the valency, what will be the valency? 8 minus 7 equal to 1. So it will be the, so for the fluorine, the valency equal to the 1. Okay. Similarly, for the fluorine, valency will be the 1. Bromine, it will be the 1. Iodine, it will be the 1. So fluorine, chlorine, bromine, iodine, it has the valency 1. It has the valency equal to 1. Similarly, if we talk about for the nitrogen case, right, so electronic configuration equal to 1s2, and this is the 2s2, and this is the 2p3. So this is the valence shell. Okay, so this valence electrons, the number of valence electron for this case equal to the 5. So equal to the 5. Now the valence equal to 8 minus 5 equal to 3. 8 minus 5 equal to the 3. So the valence equal to 3. Similarly, if you see this oxygen case, the electronic configuration 1s2 and 2s2, and this is a 2p4. So this is the valence cell. So number of valence electrons equal to 2 plus 4 equal to 6. Now the valence equal to 8 minus 6 equal to 2. So here in this array, you have to calculate the to know the electronic configuration. This is the general electronic configuration. General electronic configuration. So from that, you have to know, first of all, you have first decide, okay, so this is the valence shell. So in this valence shell, how many electrons is present? 5. So the valence equal to 8 minus 5 equal to 3. Now, nowadays, actually, this valence is defined by oxidation state. So what is that actually? So this oxidation state actually equal to the valency. Suppose the nitrogen, for the nitrogen the valency equal to 3. So now the oxidation state could be the positive and could be the negative. So that actually this sign, the positive and this negative, that sign actually vary according to the compounds. But the oxidation state for the nitrogen equal to +3. Now the this is the for the nitrogen case. Now the the oxidation state will be the -2. Because so here it is the positive. Here it is the positive. Why it is the negative? The number is the digit is the same. Oxygen valence equal to 2. So the oxidation state will be the 2. Oxidation state will be the 2. But why this negative term is coming here? Because there is the electronegativity. Electronegativity term is coming. Why it is the negative is there? There is the reason. If you see, is it the electronic configuration? For that electronic configuration, if you see this electronic configuration, I am just writing here the valence electronic configuration. This is the 2s2 and this is the 2p4. So to get the more stable electronic configuration, more stable electronic configurations will be the 2p6, but it is the 2p4. Now it is the 2p4. So it needs the 2 electrons. Then the electronic configuration will be the 2p6. Okay. So when it is taking the 2 electrons, then the oxygens will have the -2 charge. That's why the oxidation state will be the -2. The oxidation state of the oxygen will be the minus 2. Similarly, if you see the nitrogen, it is the 2p3. So there is the 3 valence equal to 3. Now it could be the positive, but it could be the negative. What will be there? So this is actually defined. So in here, this is a possible by this 3 electron gaining or the less the 3 electron. But there is a problem is that nitrogen, if you see this nitrogen case, it will be the somewhere it is the showing this plus 3 oxidation state, somewhere it is the showing the minus 3 oxidation state. That is actually depending upon the compounds, what elements is there or not. So in this way, here we have seen the valency and this oxidation state. Valency will be the oxidation state, but the oxidation state has the positive and the negative charge. It could be the plus 2, it could be the minus 2, but this positive and the negative charge actually defined. It is the gaining these electrons and the negative charge, and the positive charge is defined. It is the loss of the electrons. So that is absolutely dependent on the compounds. Now, which compounds is there or the not? So, if you take this one example here, if you see this one example, suppose I am taking the one example, this is the OF2. Okay, so between that oxygens and the fluorine, this fluorine has the more electronegativity than the oxygens. Okay, so that's why the oxygen, that's why this actually this negativity term actually coming. So here, if you see this compound OF2, this fluorine is the more electronegative than oxygen. So suppose there is oxygen, fluorine, and fluorine. This is the chemical structures of this OF. So what will be happened? So this is the bonding electrons here. Suppose this is the covalent bond. We know that this covalent bond means this bonding electrons, it is equally shared by this B and also equally shared by this A. But here, what is happening? Due to the more electronegativity of the fluorine compared to the oxygen, these bonding electrons is moved to the fluorines, actually towards the fluorines. So what is happening here? Somewhere delta negatives, and there is the delta positive charge will be created. Okay, because this bonding electrons actually it is not here. So now it is actually forming like that actually. So here actually. So that's why suppose here the negative charge is created. Here the negative charge is created because why I am putting the negative charge? Because these two electrons, one electron actually coming the oxygen, another one electron is coming the fluorine. But in this compound, these bonding electrons is maximum shared by this fluorine. Suppose 90% shared by this fluorine and 10% shared by this oxygen. That's why so more extent actually electron density is shared by this fluorine. That's why I am putting the negative charge here. Similarly, here I am putting the negative charge here. Okay. So what will be happen? So due to the two negative charge, oxygens will have the two positive charge plus 2. Okay. So in that compound, if you see the oxidation state, fluorine has the oxidation state -1 and oxygens will be the oxidation state the +2. So this is the valency of this fluorine and this is the valency of the oxygen in that compounds. If you see this another compound, suppose N2O. If you if you just taken this another compound, it is a N2O. So in this compound, if you see oxygen is the more electronegative than the nitrogen. Now what will be happened here? What will be happened here? So this is the nitrogen. Suppose this is the nitrogen. Okay. So this is the bonding electron. Now it is moving to this oxygen side. So what will be happen? It will have there are two negative charge here, two minus. Now the nitrogens will be the positive, positive will be here. So the valency of this nitrogens will be plus 1 here, and oxygens will be the minus 2 here. So in this array, you have to actually design, you have to the say, okay, so this is the valency. So here the valency, so in this compound, if you see the valency of the oxygen is changing, but it is a plus 2, but here the valency is a minus 2 because of the others and other neighboring elements, because this the neighboring on the ancillary this element is the fluorine, which is the bonded to this oxygen, which is the more electronegative than the oxygen. But here the nitrogen is the bonded to the oxygen, but the nitrogen is the less electronegative than the oxygen. That's why this bonded electrons is more close to the oxygen. Suppose here it is the sharing by 90%, it is sharing by the 10%. So when the more extended electron density is shared by the oxygen, then we have to put the negative. We have to put the negative sign. That's why, uh, that's why here the oxygen has the valency minus 2, but here the oxygen has the valency the plus 2. So in this way, you have to calculate, you have to see, okay, what will be the valency of the element of a compound. So similarly, here I have taken an one example. If you see this one problem I have taken, so using the periodic table, the predict the formulas of compounds which the might be formed by the following pairs of the elements: the silicon and the bromine, and the aluminium and the sulfur. So here the silicon and the bromine, here the aluminium and the sulfur. So what will be the compound uh, will be the made by these two elements, is the silicon and bromine, and what will be the compound will be made by this aluminum and the sulfur. So first of all, to know that, I have to see the periodic table of for that. So the silicon and this is the bromine. So silicon and the bromine. Okay. So from that, if you see the bromine, we know that the valency of that bromine, or this fluorine, chlorine, bromine iodide, this halogen element is valency equal to the 1. Okay. Now, the carbon, for that carbon, silicon, germanium, tin, and lead, this actually will have to know what will be the valency of this group, this carbon group. It will be the valency equal to the 4. How? If you know this carbon, the electronic configuration will be 1s2 and 2s2, and this is the 2p2. Okay. So, the electronic configuration, if you say this is the 2p2. So anyhow, if you see, it get this 4 electrons. So the valence equal to what will be here. This is the valence so number of the valence electron equal to 4. So the valence equal to 8 minus 4 equal to the 4. So the valency of this carbon, silicon, germanium, tin, and the lead equal to the 4. But the valency of the halogen element equal to the 1. So the carbon will be, so here the silicon will be the valency 4, and this bromine will be the valency 1. So when you know that, the valency, when you know that the valency, here again I am writing here. Suppose you know that valence. Here the valence silicon has the valency 4, bromine has the valency the 1. Now you are going to make a compound with this silicon and the bromine. So what will be the compound? So you just write here the silicon and this bromine. Okay. Then what you have to do that, the valency of this silicon, you have to put the bromine part, and the valency of this bromine, you have to put the silicon part. So the compounds will be SiBr4. That is actually compound is the forming. Okay. So first of all, you calculate the valency, then you just put in this array. Okay. So in this array, so silicon has the valency the 4, You just write it down below the bromine, uh, and you have to you know that the valency of the bromine equal to the 1. You just write down below the silicon. So it will be the chemical formula of this compound SiBr. Similarly, if you see this aluminium and the sulfur, again, if you go here, this is the aluminium. Where is the aluminium? So this is the aluminium here, and this is the sulfur, this here. Now this aluminium, what will be the valency? So the valence electrons, the number of the valence electrons will be the 3. So it has the valency 5. Now the sulfur, what will be the valence? So it will be valence electron equal to 6. So it is a 2. So 5 and 2. So aluminum case, what will be no, sorry, just 1 minute. It will be the 3. Sorry, it will be the 5. So it will be the 3. Okay, because boron has the electronic configuration 1s2, 2s2, and 2p1. Uh, okay, just a minute. 3. Okay. So it will be no. So for that aluminum case, actually, if you see that here, this is the belongs to the 13th group, belongs to the 13th group. So valence equal to the 3. It will have the valence equal to 3 because the number of the valence electron will be the 5. Okay, because the 1 is 2 and this is the 2 is 2 and this is the 2p1. So the valence equal to this 3, and this sulfur, it is a 16 electron group. So valence equal to the 2. So here the aluminium has the valence equal to 3, oxygen is valence equal to 2. Now you have to make the compound. So it will be here and it will be here. To the sorry, it will be the sulfur. So the compound will be the Al2S3 and the chemical formula. So this is will be the chemical formula Al2S3, which is the made by this aluminum and the sulfur. Next, there is the some examples just I have taken here. If you see, uh, this is the lithium, sodium, potassium. This is the hydride compounds. Calcium, B2H6, aluminum hydride. So these are the periodic chains of the valence of the element as shown by these formulas of their the compound. So these are actually a formula of the hydride, and these are actually formula of the oxide. If you see here, the sodium case, if you see this lithium case, we know that the lithium has the valence equal to plus 1. So here, this is the 1. So lithium will have the plus 1, and this oxygens will be the minus 2. Okay, so in this way, you have to similarly for this N2O, N2O. So oxygen will be the 1. So the sodium will be the valency plus 1, or the oxidation state will be the plus 1, and the oxygens will have the oxidation state will be the minus 2. Okay, similarly, if you see this B2O3, so borons will have the oxidation state plus 3, and oxygens will be the oxidation state will be the minus 3. Boron has the valence actually plus 3. Boron, aluminium, gallium. So this is the actually 30 group elements. So another thing we have to know, anomalous properties of the second periodic element. So this is a very interesting thing. What is actually talking about here? Just I am writing here anomalous properties of the second period element. Second period elements, if you say this is the lithium, beryllium, boron. Uh, so here there is the diagonal strip is the properties. Okay. So what is I am saying here? This is the only the lithium and the beryllium. These the two compounds actually forming this covalent bond. And what about these other elements is there? These element actually forming this ionic. So these two compounds actually forming the covalent bond. Okay. But these other compounds, other elements actually forms ionic, ionic bond. So with that actually compounds, so with that the elements, if you see the some chemical properties is matching with this magnesium, similarly Berylliums also the some properties, ionic character, atomic characters, and some of the physical properties, ionization enthalpy, electron enthalpy also matches with this aluminium. So this match actually is designed by this diagonal relationship. So it is actually the diagonal relationship. Okay. So similarly, if you see that lithium, magnesium, so here another thing we can say, if you see the first member uh, for that boron case. Okay. So if you see this boron, it has the maximum valency. That's why I'm telling equal to the plus 5. How 1 is 2, 2 is 2, and 2p1. So the valence electrons will be the 3. Okay. So what is happening here? So 8 minus 3 equal to the 5. So this is the maximum valence equal to the 5 for that boron. Okay. So when we are talking about this boron, then the maximum valence equal to 5, then the corresponding compound, it can be BF4 minus. How this valence equal to 5? This is the 4 fluoride and 1 negative charge. That's why the valence equal to the 5. Similarly, if you go to this second, if you go to this second period, this is the aluminium. For that aluminium case, the maximum valency will be the 9. Okay, so that corresponding compounds will be the AlPF6 3 minus. So here this fluorine will be the 6. So this is the 6 fluorine, and there is the 3 negative charge. So that's why the maximum valency is changing when we are going to this another period from this boron to the aluminium. Now we will talk about, suppose here one example I have just given here for a propylene. Uh, what will be the oxidation state and the covalency of this aluminium in this compound? Okay, so first of all, you have to calculate the oxidation state. So to calculate this oxidation state, what is happening? So this is actually one type of the metal complex. So suppose this is the aluminium, here the main group element, chlorine also the main group element. Suppose I am taking this is as a ligand and water also as a ligand. Okay, but this Cl actually, this is the ionic ligand, and this is the water. This is actually the neutral ligand. When we are talking about this the ionic ligand, that means it gives the minus one charge. When we are talking about this neutral ligand, it gives the zero charge. So here the number of the chlorine equal to the one. Okay, so it actually gives this minus one. But here the water is the neutral, so it is giving the charge equal to the zero into 5 because there is a 5 water molecules is there. So it is actually giving the zero charge. But there is the two anion is present outer sphere area. So that's why it has actually metal complex has the plus 2 oxidation state. Sorry, metal complex has the plus 2 charge. But what is the oxidation state of this aluminium? To calculate the oxidation state aluminium, you have to write down here. Suppose I am consider the oxidation state of the aluminium equal to the X. So X plus minus 1, this minus 1 for this chlorine plus 5 into 0. This is for this water. Okay, now what will be here? So this is actually giving plus 2 charge. So it is actually plus 2. So equal to plus 2. So here if you see the X equal to plus 2 plus 1 equal to plus 3. So the oxidation state will be the plus 3 of this element. Aluminum has the oxidation state equal to plus 3. Now the covalency means how many here, actually how many ligands is present. This is the 5 and this is the 1. That's why this is a covalence equal to the 6. Now I will talk about the chemical reactivity. The chemical reactivity of elements. So, in our previous class, if you can see that we already know uh, about the physical properties. So, what physical properties actually we know? We know the atomic radius, we know the ionic radius, we know the shielding effect, and also we know that ionization, enthalpy, then the electron gain enthalpy, then we know about the electronegativity. So these actually physical properties actually we have know, and also we have known the how these physical properties actually changing when we are going to this left to right, or when we are going to this up to down. Okay, how this atomic radius, ionic radius, and this shielding effect, ionization enthalpy, and this electron gain enthalpy and electronegativity, how actually that changed. Now we will know about the chemical properties. So why I am written here, this this physical, this chemical properties. When we will talk about this chemical reactivity, this chemical reactivity also depends or the correlated with these physical properties. How? Just you just see that when we are going to left to right, then what is happening? The atomic size actually decreased, because we know that when we are going to the left to right, then the principal quantum number remains the same, but the number of electrons is the increasing. When this number of electrons is the increasing, but the principal quantum number is the same, then it is creating the more actually uh, Z effective, but the Z effective value, the effective nuclear charge value actually the increasing. When the Z star, this Z effective nuclear charge is value, this value is increasing, then the atomic size or the atomic radius, is the atomic radius is decreasing. When this atomic radius is decreasing, what is happening here? The electron ionization enthalpy, ionization enthalpy value decreased. Sorry. Ionization enthalpy value is increased. Why? Ionization enthalpy means that to remove one electron from the valence shell, how much amount energy it is the needed. That is called the ionization enthalpy. So when this jet start, the effective nuclear charge value is increasing. That means that outer shell electrons is more. There is a more attractions by this nucleus. That's why this ionization enthalpy is increasing. This actually physical properties then already I already taught in the previous lectures. So here just I am uh, uh, just telling to correlate how these chemical properties and the physical properties is related. So ionization enthalpy is increasing. When this ionization enthalpy is increasing, then what is happening when we are going to this left right, the electron gain enthalpy is more negative. That means that right side, whatever right side element is here, uh, this actually has the more negative electron gain enthalpy. But this left side element has the electropositive, uh, electropositive electron gain enthalpy. But if you, instead of that noble gas or the inert gas element, it has the positive electron gain enthalpy. Instead that actually, if you don't consider this element here, because they are the inert, because they do not want to react with this other element. So here we are actually not considering this element. So without that element, this right side elements will have the more negative electrogen enthalpy, and left side elements will have the more positive electrogen enthalpy. So this negative electrogen enthalpy means that it can easily take the electrons, but this positive electrogen enthalpy means that it do not take easily the electrons. It can easily remove these electrons. Okay, so this right side element has the more negative electron gain enthalpy, and the left side element has the more positive electron gain enthalpy. That's why this element actually, this element easily, easily, not easily take the electrons. It can easily remove these electrons. So when this it can remove these electrons, that means that it acts as a uh, reducing agent. That means it can reduce another body easily, but it will be the oxidized. So that's why it is a reducing agent. Then it will be the oxidizing agent. Okay. So that's why when we will talk about this chemical reactivity, then left side elements and the right side elements are the more reactive. But this central part, this central element actually, the reactivity is the very, very low. This is the low reactive, low reactive. This is the center element. Whatever element is there. Okay. So these are actually very, 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 very reactivities are very, very less. But this left side and this right side, these two element actually the activity is the high. So the pattern will be the different. Patterns will be the different because here it is act as a reducing agent. It is act as the oxidizing agent. So this pattern is the different, but they are the reactive. But compared to this central element, they are not the reactive compared to the left side and the right side element. So here one example, just as a problem I have given here. Is so by chemical reactions with the water, N2O is a basic oxide and Cl2O7 is a acidic oxide. So this is actually defined by like that actually because we know that this is the left side element, this is the sodium, this is the right side element, is the oxygen. So when they actually reacting to each other, because both are more the reactive, then they are forming this N2O. So this is the one type of the oxide. But this oxide could be basic or it could be the acidic. Okay, that is actually defined when this N2O react with this another body, suppose the B, and it is forming the base, then it will be the basic, but or it forming the acid, then it will be the acidic. Here, if you see this N2O, this is N2O, when reacting with this H2O, it is forming this NOH, sodium hydroxide. This is actually the base. It is the form the strong base. Uh, that's why it is. We can say this oxide is the basic oxide. Uh, uh, so that's why it is a basic oxide. But for that Cl2O7, when it is reacting with this water, it is forming HClO4. So this is the actually acid, hydrochloric acid. So sorry, this is not the hydrochloric acid, this is the hydrochloroparacid. So this is the acid. That's why this oxide actually the acidic. Otherwise, we can also the taste by the litmus paper. If you just touch with this oxide and this oxide, when it is a basic, then these litmus papers will be the green. Uh, that will be the more green, or it will be the more basic. Then it will be give the blue. Uh, but but in the litmus paper, the Cl2O7 will be the red, uh, red color because it is the acidic. So in this way, you can say, oh, this is the acidic and this is the basic the oxide by the litmus paper state, or you can also react with this water and the see which actually is forming. It is forming the base, then it is a basic, and it is a forming the acid, then it is the acidic. So here I am going to actually stop this class. But before the finishing this class, just I am what I actually teach uh, uh, of this periodic table class. Well, this is the fifth class. So in that first class, if you see that, if you can remember, in that first class, just I am talking about this history of the periodic table. Okay, history of the periodic table. So there are some of the histories there. Second thing we have talking about the modern periodic table. Okay, this is the modern periodic table. How this modern periodic table actually came here. Third thing, what I am talking about. So in this modern periodic table, how this number of groups, how many groups is there, how many periods is there, and also S block, P block elements, D block elements, which are the actually alkali metal, hmm, which are actually the alkaline earth metal, which is the transition metal, which is the inner transition metal. So there is a classification of this metal and how this metal actually has been arranged in this periodic table that actually I have teach in this class. Then we have talking about the some physical properties. Okay, so this is the very important. This is the physical properties, uh, and how these physical properties actually correlated from this according to the period and the group. But if you take these physical properties, before going to these physical properties, there is the some important and topic. Uh, First is the shielding effect. Okay, what is the shielding effect? Then the sigma, what is the shielding constant? How it is actually calculated? Then we have talking about the Z star or the Z effective. This is called the effective nuclear charge. This is called the effective nuclear charge. Okay, so according to that value, this is the Z effective or the effective nuclear charge. We already talking about the atomic radius, the trend of the atomic radius. Then we are talking about this is the ionic radius. Okay, this ionic radius. Then we are talking about ionization enthalpy, electron gain enthalpy. This is the electron gain enthalpy, and this electronegativity also. Metallic character, non-metallic character. So these are the physical properties, and indeed in that class, I have talking about the valency and the oxidation state, and the some chemical properties is there. So overall, if you say in this class, in this chapter, what I have talking about. So this actually the modern periodic table. Then this is the classification. This actually the history is there. S block, P block element, and also and also the nomenclature is there. And in the third class, there is a Z effective. Uh, and electronegativity in the periodic trends, metallic, covalent radius. So this actually on the whatever topics in mentioned in CRT book. So according to that, I have teach here. So after that, I will just talk about some MCQ question. Here we can see that. Just give me time to share. Start. Okay. So here you can see that this is the one MCQ question is that uh, who actually gave the idea for the first time to classify the element as per their the properties. This element actually, so this actually properties is actually meaning the physical properties. Okay, this is actually physical properties. Who has given? This is the Roberian. This Roberian actually has given first how to classify this element according they are the physical properties. Like physical properties is here means the physical state actually. So it will be solid, liquid, and the gas. So according to that physical properties, actually this Tugerian classify the elements. Second question is that in the triads, uh, the average weight of the first and the third elements are equal to the second one. So this is actually uh, just it need time. So this is actually true because if you see this first and the third element, uh, the average weight of this element are equal to the second one because when we are going to first element, then the second element, and then the third element. So there are the physical properties actually the changing. So that's why this whatever atomic weight is there, second also is there and third also is there. So it is the mention here. So third is that each of the following is not the Doberian trat. That means that in that trat, which actually is not following. So this is actually helium, sodium, and argon because we know that hydrogen, helium is there, then the lithium is there, then the sodium is there, then the boron is actually coming here. So that's why, and argon is here. So that's why the helium and the sodium is okay, but this argon is more the far away. So that's why this option will be the correct. Similar thing, the properties of the every eight elements is the similar to that of the first element. This is the proposed by John's Alexander Newland. Already I have taught this is the eight elements. Whatever, because if you see the number of eight electrons after this number of eight electrons, this element actually the coming. Okay, so if you see the sodium, if you see the hydrogen, then the helium, then the lithium, then again it is actually the coming uh, beryllium, but here is the sodium is coming. So this lithium and the sodium, this the eight electrons, the difference is there. So that's why this eight electrons difference is coming. That's why the difference is coming here. Then it is that the lithium and the sodium is coming in the same group. Then it will have the same type of the physical properties. Then the Newton's law of the octaves is only the valid until the calcium. It is actually the true because that time after that there is the not so much the electrons actually has not discovered. Then if you see the periodic function of the are the properties of the respective element, so it will be the atomic weight because according to this atomic weight actually they have classified this element. That's why Eka aluminium is a galvanium. So this is the naming of this another name of the gallium. Another thing is the what are the atomic weight of the Eka, silicon, and the germanium. So it will be the 72 and the 72.6 because the Eka silicon and the germanium. In the Mendelic periodic classification, what is the number of the groups? So how many groups is there? We know that eight groups is there. And the ideal gas where in the group of the Mendeleev periodic tables, and we know that the ideal gas, that means that noble gas actually, the inert actually gas is there. So this is actually fourth. Uh, this is the first group is there. When we are talking about this Mendeleev periodic tables, then the first groups, if you see that the ideal gases were in the group. So with this first group, hydrogen, then the helium. So this helium actually is the present is here. Okay, so in this first group, these are actually present. So here I have just discussed the 10 MCQ questions of that according to the first lectures. So similarly, if I discuss the another MCQ question, uh, just give me time. Okay. So that one actually for the class 2 MCQ. So that we who actually discovered this X-ray characterize, that is actually discovered by this Henry. Second, this group of that versus actually that gives the straight line. That is actually true because there is the plot is there. Okay. In this X-ray, if you see, this is versus the when we are talking about the J, that it is the giving like that. So the physical properties and the chemical properties of an element are the periodic function of its. This is the atomic number. When we are talking about this physical properties and the chemical properties, because according to this atomic number, they have the classified it. Sorry. Then what does the Z actually? This Z actually, what is actually defined here? This is defined. This is the atomic number. When we are because in the second question and the fourth question, both are the similarly same. If you see this Henry, his law is given by this equation. Okay, what do the A and the B that represents the here? This is actually defined by this. This is the A and this is the B. This is defined by this proportionality constant. A is the proportionality constant and B is the screening constant. Actually, here this screening constant is actually B actually defined by this sigma. In this class, already I am talking about this is the sigma. This is the screening constant of the shielding constant. The horizontal rows in the Bernoulli periodic tables are called. This is the series. Actually, this is the periods. This is not a period. This is the group. This is the series. Because if you take this Mendeleev's the periodic table, it's the horizontal lines is there. That's one. That is actually called is the periods. It will be the periods, or it will called also the series also. So that's why they both actually the right here. In the modern, the long form of the periodic tables, the horizontal row and the verticals the column as is. So here, if you see this the horizontal row, this is a horizontal and this is a vertical. So this vertical actually defined by these groups, and this is the vertical is the groups, and this the horizontal is defined by this period. So B will be the right answer. And this periods, the number the corresponding to the highest, if you see the principal quantum number. When we are talking about this period, that means that one. So that periods means when we are talking about suppose the carbon. Okay. So carbons, the number of periods equal to 2. So the principal quantum number equal to 2. Okay. When talking about the nickel, its period equal to 3. So the principal quantum number, if you see, it's n equal to the 3. Okay. So in this way, so according to the principal quantum number, the highest the principal quantum numbers will be the period. Which was the incomplete period in the long form of the modern periodic table. If you see this modern periodic tables, the which period actually incomplete? This is actually seventh period is not the complete. And which of the following the period is the shortest one? Which is the very short? That means there is the very short. If you see this hydrogens and the helium. Okay. So in this period, actually, there is a two elements is there. So that's why this first period is the very short. So in this way, here I am covered the two MCQ session, and also I have completed this chapter in this class. So now I am going to stop on this class. Thank you very much.